essentially what happened before the Big Bang. Right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it.
Apophis, discovered in 2004, is a near-Earth object with a diameter of approximately 340 meters. Named after the Egyptian god of chaos, its potential energy, if it were to collide with Earth, is estimated to be over 800 megatons of TNT, which is more than 15 times the explosive force of the most powerful nuclear bomb ever detonated. The immediate impact of such a collision would be catastrophic, creating a massive crater and triggering powerful earthquakes. The force of the impact would flatten buildings, vaporize surroundings, and produce an immense shock wave capable of leveling cities and forests far beyond the initial impact site. Moreover, the collision would eject a huge amount of dust and debris into the atmosphere, leading to what scientists call an impact winter. This phenomenon would block sunlight for an extended period, causing a significant drop in global temperatures. The resulting cold and darkness would disrupt agriculture, potentially leading to a period of worldwide famine and ecological collapse. Initially, there was concern that Apophis might collide with Earth in 2029, but further observations have ruled out this risk for at least the next century. In response to the threat posed by near-Earth objects like Apophis, scientists are developing strategies for planetary defense. These include early detection systems to identify potential threats long before they can impact Earth, as well as missions designed to deflect asteroids away from our planet. One such mission is NASA's Double Asteroid Redirection Test, DART, which aims to demonstrate the capability of altering the trajectory of an asteroid by impacting it with a spacecraft. The success of such missions is crucial for developing effective defense mechanisms against potential asteroid impacts in the future. The discovery of Apophis and its potential impact has captured the public imagination and inspired discussions about humanity's vulnerability to cosmic events. The realization that such a relatively small object could cause widespread devastation highlights the importance of taking proactive measures to protect our planet. In addition to technological solutions, international cooperation is essential for addressing the threat of near-Earth objects. Collaborative efforts between space agencies, governments, and scientific institutions can enhance our ability to detect, track, and mitigate the risks posed by these cosmic hazards. Educational and public outreach programs also play a vital role in raising awareness about the threat of near-Earth objects and the importance of planetary defense. By informing the public about the risks and the steps being taken to address them, these programs can foster a greater understanding and support for efforts to protect our planet from potential asteroid impacts. Voyager 1, launched by NASA on September 5, 1977, is an iconic symbol of human ingenuity and our quest to explore the unknown. It was part of the Voyager program, which also included its twin, Voyager 2. Both spacecraft were designed to take advantage of a rare planetary alignment that allowed them to slingshot from one outer planet to the next using a gravity assist, thus saving on fuel and reducing travel time. Initially, Voyager 1's primary mission was to explore the outer planets, Jupiter and Saturn, and send back unprecedented data about these distant worlds. The spacecraft, equipped with a suite of scientific instruments, including cameras, magnetometers, and spectrometers, sent back stunning images and valuable data. Among its many achievements, Voyager 1 provided the first detailed images of Jupiter's Great Red Spot and Saturn's intricate ring system. Its discoveries about the atmospheres, moons, and magnetospheres of these gas giants have significantly advanced our understanding of the outer solar system. Voyager 1's mission didn't end with Saturn. After its flyby, the spacecraft was put on a trajectory to take it out of the solar system. It continued to send data back to Earth as it ventured further into the unknown, becoming the first human-made object to enter interstellar space on August 25, 2012. At that time, it was about 121 astronomical units, AU, from the Sun, where 1 AU is the average distance between Earth and the Sun. The transition into interstellar space was marked by a sharp increase in cosmic rays detected by Voyager's instruments. This indicated that the spacecraft had passed beyond the heliosphere, the bubble of solar wind and magnetic fields emanating from the Sun, into the interstellar medium, the space between stars filled with gas, dust, and cosmic rays. This milestone was a testament to the durability and design of the spacecraft, which continues to operate long beyond its expected mission lifetime. The scientific legacy of Voyager 1 is immense. Its instruments have provided valuable data about the boundary of the heliosphere and the nature of the interstellar medium. These insights help scientists understand more about the environment that surrounds our solar system and influences cosmic phenomena. The data Voyager continues to send back will be analyzed for years to come, providing a wealth of information for future generations of researchers. The journey of Voyager 1 symbolizes humanity's desire to push boundaries and explore the unknown. It represents a remarkable achievement in engineering and space exploration, showcasing our ability to reach beyond the confines of our planet and send a piece of ourselves into the vastness of space. Despite being launched over 4 decades ago, Voyager 1 continues to operate and send back data, a testament to the ingenuity and vision of the scientists and engineers who designed and built it. Moreover, Voyager 1's mission has inspired countless people around the world, fostering a sense of wonder and curiosity about the cosmos. It serves as a reminder of what humanity can achieve when we work together towards common goals and embrace the spirit of exploration. The spacecraft's continued journey through interstellar space will likely continue to captivate and inspire future generations, reminding us of the vastness of the universe and our place within it. Earth's magnetic field has experienced numerous reversals throughout geological history, where the magnetic north and south poles switch places. These geomagnetic reversals occur over thousands to millions of years, and are driven by changes in the flow of molten iron within Earth's outer core. The last known reversal, known as the Brune-Matsuyama reversal, happened approximately 780,000 years ago. During a reversal, the magnetic field weakens significantly, which leads to several potential consequences. One of the main effects of a weakened magnetic field is increased exposure to cosmic rays and solar radiation. The magnetic field acts as a shield that deflects charged particles from the Sun and cosmic rays from space. When the field weakens, more of these particles can reach the Earth's surface, leading to higher radiation levels. This increase in radiation can have several biological and technological impacts. For migratory birds, marine turtles, and other species that use Earth's magnetic field for navigation, a reversal could cause significant disruptions. These animals rely on the magnetic field to orient themselves and migrate over long distances. A weakened and fluctuating magnetic field might confuse their navigation systems, leading to disorientation and potential impacts on their migration patterns and survival rates. In addition to biological effects, geomagnetic reversals can also impact technology. Satellites and other space-based systems are particularly vulnerable to increased radiation levels. Higher exposure to cosmic rays and solar radiation can damage electronic components, interfere with satellite communications, and shorten the operational lifespan of these systems. Power grids on Earth are also at risk, as geomagnetic storms during periods of weak magnetic fields can induce currents in power lines, leading to voltage instability and potential blackouts. Overall, while a geomagnetic reversal is a natural part of Earth's geological history, it presents several challenges for both biological systems and modern technology. Understanding these impacts and developing strategies to mitigate them is essential as we continue to study and prepare for future geomagnetic reversals. Antares is a red supergiant star located in the constellation Scorpius. It is one of the largest and brightest stars visible to the naked eye, making it a prominent feature in the night sky. Antares is nearing the end of its life cycle, and astronomers predict that it will eventually go supernova. When it does, the explosion will be a spectacular event visible from Earth, potentially rivaling the brightness of the full moon. This supernova would illuminate the night sky for weeks or even months, offering a rare celestial display. Despite its dramatic nature, the Antares supernova poses no direct threat to Earth. Located about 600 light-years away, the distance is sufficient to prevent harmful radiation or debris from affecting our planet. Instead, this event will provide a unique opportunity for scientists to study the processes involved in the death of massive stars. Supernovae are key events in the cosmic cycle of matter, as they create and disperse elements essential for the formation of new stars and planets. The explosion of Antares will allow scientists to observe and analyze various stages of the supernova process, from the initial collapse of the star's core to the subsequent blast wave and the formation of a remnant, such as a neutron star or black hole. This will enhance our understanding of stellar life cycles, nucleosynthesis, the creation of new elements within stars, and the dynamics of supernova explosions. Additionally, studying the light curve and spectra of the Antares supernova can provide insights into the properties of the progenitor star, the composition of the ejected material, and the mechanisms driving the explosion. Observations from ground-based telescopes and space-based observatories will be crucial in capturing detailed data on this event. Saturn's rings, one of the most iconic features in our solar system, are gradually disappearing. Scientists estimate that these magnificent rings may last only another 100 to 300 million years. The primary reason for the rings' dissipation is a process known as ring rain. In this process, the ring material, which consists of ice and rock particles, gradually falls into Saturn's atmosphere. This ring rain is driven by Saturn's gravity, as well as interactions with the planet's magnetic field and radiation from the Sun. As the particles from the rings enter Saturn's atmosphere, they vaporize, creating a faint, icy drizzle that extends from the inner edge of the rings down to the planet. This continuous loss of ring material will eventually deplete the rings, leading to their disappearance. The loss of Saturn's rings will dramatically change the planet's appearance and characteristics. Saturn, which is currently distinguished by its bright and expansive ring system, will transform to resemble the other gas giants in our solar system, such as Jupiter, Uranus, and Neptune, which either lack prominent rings or have much fainter ones. Mars's moon Phobos is gradually spiraling inward towards the planet due to tidal interactions, and it is expected to reach the Roche limit in approximately 30 to 50 million years. The Roche limit is the distance within which a celestial body, held together primarily by its own gravity, will begin to disintegrate due to the tidal forces exerted by the planet it orbits. Once Phobos reaches this critical distance, the tidal forces from Mars will become strong enough to tear the Moon apart. This disintegration will result in the formation of a ring-like structure around Mars, as the Moon breaks apart into smaller pieces that gradually spread out and form a ring system. The formation of these rings could take thousands to millions of years, as the debris from Phobos settles into a stable orbit around Mars. Unlike Saturn's bright and extensive rings, the rings around Mars would likely be narrower and less visible from Earth, but they would still provide an intriguing feature for observation and study. The resulting rings would be less expansive and less massive than Saturn's iconic rings, but they would still be a remarkable spectacle. The formation of rings around Mars would also have potential implications for the planet's other moon, Deimos, and their orbits. The gravitational interactions between the newly formed rings, Deimos, and Mars could alter their orbits and potentially lead to further changes in the Martian system. These interactions would be complex and could result in shifts in the orbits of Deimos and other debris, potentially leading to collisions or ejections of material from the system. Overall, the disintegration of Phobos and the subsequent formation of rings around Mars highlights the dynamic and ever-changing nature of our solar system. This process provides a fascinating example of how celestial bodies interact and evolve over long periods, offering valuable insights into the mechanisms driving planetary and moon systems. The study of these interactions helps scientists understand the long-term stability and evolution of planetary systems, shedding light on the processes that shape the diverse and dynamic environments within our solar system. The potential disintegration of Phobos and the formation of rings around Mars also underscore the importance of continued observation and study of our solar system's moons and planets. By monitoring the orbits and interactions of these celestial bodies, scientists can gain a better understanding of their evolutionary pathways and the forces that influence their behavior. This knowledge is crucial for developing accurate models of planetary system dynamics and predicting future changes in their structure. Furthermore, the study of Phobos and its eventual disintegration can provide insights into similar processes that may occur in other planetary systems. Observations of exoplanets and their moons can reveal whether similar tidal interactions and ring formations are taking place elsewhere in the universe, contributing to our broader understanding of cosmic phenomena. An extinction-level asteroid impact refers to a collision with an object larger than 5 to 10 kilometers in diameter, capable of causing catastrophic devastation on a global scale. The initial explosion from such an impact would create a massive crater, ejecting vast amounts of debris into the atmosphere. The kinetic energy released upon impact would be equivalent to millions of nuclear bombs detonating simultaneously, leading to widespread destruction. The immediate effects of an asteroid impact of this magnitude would be catastrophic. The intense heat generated by the explosion would ignite wildfires over large areas, setting forests and grasslands ablaze. The resulting shockwave would trigger powerful earthquakes, further destabilizing the affected regions. If the impact occurs in an ocean, it would generate massive tsunamis, inundating coastal areas and causing extensive damage. The force of the impact would vaporize everything in the immediate vicinity, flatten buildings, and produce an immense shockwave capable of leveling cities and forests far beyond the initial impact site. One of the most significant long-term consequences of an asteroid impact is the phenomenon known as impact winter. The debris and dust ejected into the atmosphere would block sunlight for an extended period, potentially lasting months or even years. This blockage would lead to a dramatic drop in global temperatures, severely disrupting weather patterns and agricultural productivity. The resulting cold and darkness could cause widespread crop failures and food shortages, leading to famine and societal collapse. The environmental changes induced by the impact winter could persist for years, drastically altering ecosystems and putting immense strain on the survival of many species. The combination of these immediate and long-term effects could result in mass extinctions, similar to the event that wiped out the dinosaurs approximately 66 million years ago. The Chicxulub impact, which created a crater over 150 kilometers in diameter in what is now Mexico's Yucatan Peninsula, is believed to have been the primary cause of the Cretaceous-Paleogene extinction event. This event led to the extinction of about 75% of all species on Earth, including the non-avian dinosaurs. The aftermath of such an impact demonstrates the potential for an extinction-level event to drastically alter life on Earth, erasing entire species and reshaping ecosystems. In response to the threat posed by near-Earth objects like potential extinction-level asteroids, scientists are developing strategies for planetary defense. These strategies include early detection systems to identify potential threats long before they can impact Earth and missions designed to deflect asteroids away from our planet. Technologies such as space-based telescopes and radar systems are being employed to track and monitor asteroids that come close to Earth's orbit. One notable mission is NASA's Double Asteroid Redirection Test, DART, which aims to demonstrate the capability of altering the trajectory of an asteroid by impacting it with a spacecraft. The success of such missions is crucial for developing effective defense mechanisms against potential asteroid impacts in the future. The discovery of potential extinction-level asteroids and their potential impacts has captured the public imagination and inspired discussions about humanity's vulnerability to cosmic events. It underscores the importance of taking proactive measures to protect our planet from such catastrophic threats. In addition to technological solutions, international cooperation is essential for addressing the threat of near-Earth objects. Collaborative efforts between space agencies, governments, and scientific institutions enhance our ability to detect, track, and mitigate the risks posed by these cosmic hazards. Educational and public outreach programs also play a vital role in raising awareness about the threat of near-Earth objects and the importance of planetary defense. By informing the public about the risks and the steps being taken to address them, these programs can foster greater understanding and support for efforts to protect our planet from potential asteroid impacts. Gamma-ray bursts, GRBs, are among the most powerful and energetic events in the universe. These intense flashes of gamma rays can release more energy in a matter of seconds than the Sun will emit over its entire 10 billion-year lifetime. GRBs are typically associated with the collapse of massive stars or the merging of neutron stars, resulting in a violent explosion that emits a concentrated beam of gamma radiation. If a GRB were to occur relatively close to Earth and be directed towards our planet, the effects could be catastrophic. One of the most immediate and severe consequences would be the depletion of the ozone layer. The intense gamma radiation would break down ozone molecules in the stratosphere, significantly reducing the layer that protects life on Earth from harmful ultraviolet, UV, radiation. An increase in UV radiation exposure could lead to higher rates of skin cancer, cataracts, and other health issues for humans, as well as damaging effects on ecosystems, particularly affecting phytoplankton at the base of the oceanic food chain. The ecological disruptions caused by a GRB would extend beyond increased UV radiation. The initial burst of gamma rays and the subsequent atmospheric changes could impact biological systems and technology. For example, increased radiation levels could affect the DNA of living organisms, leading to mutations and potential long-term effects on species populations. Additionally, the burst could interfere with satellite communications, GPS systems, and other technologies that are sensitive to radiation. Atmospheric changes resulting from a GRB could also lead to climatic shifts. The depletion of the ozone layer and the introduction of nitrogen oxides into the atmosphere could lead to a phenomenon known as a GRB winter. This is characterized by significant cooling of the Earth's surface due to the blockage of sunlight by atmospheric particles, similar to the impact winter caused by a large asteroid impact. The cooling effect could disrupt weather patterns, leading to agricultural challenges and potential food shortages. A nearby GRB directed at Earth could have profound and far-reaching impacts, including ozone layer depletion, increased UV radiation exposure, ecological and biological disruptions, technological interference, and climatic shifts. Understanding the potential risks and developing strategies to mitigate them is essential for protecting our planet from such rare but devastating cosmic events. The collision between the Milky Way and Andromeda galaxies is a significant cosmic event predicted to occur in about 4 to 5 billion years. As these two massive galaxies approach each other, the initial gravitational interactions will begin to stretch stars into long, thin streams known as tidal tails. These tidal tails are formed from stars and gas being pulled out of their original galaxies due to the immense gravitational forces at play. As the two galaxies continue to merge, the interaction will trigger bursts of star formation. The collision will cause the gas and dust within the galaxies to compress, leading to the rapid formation of new stars. This starburst phase will result in the creation of numerous new stars, giving the merging galaxies a temporary increase in brightness. Eventually, the Milky Way and Andromeda will fully merge, resulting in the formation of a new elliptical galaxy. This new galaxy, sometimes referred to as Milkomeda or Milkromeda, will have a different structure from the original spiral galaxies. Instead of the distinct spiral arms of the Milky Way and Andromeda, the resulting elliptical galaxy will have a more rounded and diffuse appearance. One of the most significant aspects of this galactic collision is the eventual merging of the supermassive black holes at the centers of both galaxies. Each galaxy currently contains a supermassive black hole, with the Milky Way's black hole known as Sagittarius A, and Andromeda's black hole referred to as P2. As the galaxies merge, the supermassive black holes will gradually move towards each other and eventually combine, forming an even more massive black hole at the center of the new galaxy. Despite the dramatic nature of this cosmic event, the distances between individual stars within the galaxies are so vast that the likelihood of direct stellar collisions is relatively low. Most of the changes will occur on a large scale, affecting the overall structure and dynamics of the galaxies rather than resulting in widespread destruction of individual stars and planetary systems. The collision between the Milky Way and Andromeda galaxies will be a monumental event in the evolution of our galactic neighborhood. It will transform the structures of both galaxies, trigger new star formation, and result in the merging of supermassive black holes, ultimately leading to the creation of a new elliptical galaxy. This event provides a fascinating glimpse into the dynamic and ever-changing nature of the cosmos. Earth's rotation is gradually slowing down, resulting in an incremental increase in the length of our days. This phenomenon is primarily driven by tidal friction, caused by the gravitational interaction between Earth and the Moon. As the Moon orbits Earth, its gravitational pull creates tidal bulges in Earth's oceans. Due to Earth's rotation, these bulges are slightly ahead of the Moon. The gravitational interaction between the Moon and these bulges creates a torque that transfers angular momentum from Earth to the Moon, gradually slowing Earth's rotation. The slowing of Earth's rotation leads to an increase in the length of our days by about 1.7 milliseconds per century. While this change is imperceptible over short periods, it becomes significant over millions of years. For instance, when dinosaurs roamed the Earth approximately 100 million years ago, a day was about 23 hours long. This gradual lengthening of days reflects the dynamic and ever-changing forces acting upon our planet. The process of tidal friction involves complex interactions between Earth's oceans and the gravitational pull of the Moon. As the tidal bulges move, they create friction with the ocean floor, dissipating energy and gradually reducing Earth's rotational speed. This energy transfer also causes the Moon to slowly drift away from Earth at a rate of about 3.8 centimeters per year. Over millions of years, this process will continue to alter the Earth-Moon system, affecting both the length of Earth's days and the distance between the two celestial bodies. In addition to the tidal interactions with the Moon, Earth's rotation is influenced by gravitational interactions with the Sun and other planets in the solar system. These interactions cause slight variations in Earth's orbit and axial tilt, which can affect rotational speed over long time scales. Moreover, internal processes within Earth, such as the redistribution of mass due to geological activity, can also impact rotation. Events like earthquakes, volcanic eruptions, and glacial melting can shift Earth's mass distribution, leading to subtle changes in rotational dynamics. The gradual slowing of Earth's rotation highlights the intricate and delicate balance of gravitational forces that govern the movements and behaviors of celestial bodies within our solar system. Over millions of years, the lengthening of Earth's days will continue, subtly but steadily altering the rhythm of our planet. This slow change has implications for various natural processes, including climate patterns, ocean circulation, and the biological rhythms of organisms that have evolved in response to Earth's rotational cycle. Understanding the mechanisms behind the gradual lengthening of Earth's days provides valuable insights into the long-term dynamics of our planet and its interactions with celestial neighbors. It also underscores the importance of studying and monitoring these processes to better predict and understand changes in Earth's environment over geological timescales. Overall, the ongoing and ever-changing nature of Earth's rotation reflects the dynamic forces at play within our solar system. The interplay between gravitational interactions, tidal forces, and internal processes shapes the evolution of Earth's rotation, influencing the length of our days and the broader environment in which we live. This phenomenon serves as a reminder of the intricate and interconnected nature of the cosmos, where even the smallest changes can have far-reaching impacts over vast stretches of time. The Sun, like all stars, has a life cycle that spans billions of years. Currently, it is in the middle of its main sequence phase, where it burns hydrogen in its core to produce energy. However, this phase will not last forever. In about 5 billion years, the Sun will exhaust its hydrogen fuel and enter the next stage of its life cycle, known as the red giant phase. As the Sun's core runs out of hydrogen, nuclear fusion will cease, causing the core to contract under gravity. This contraction will increase the core's temperature, leading to the fusion of hydrogen in a shell surrounding the core. The energy produced by this shell fusion will cause the Sun's outer layers to expand dramatically. As it expands, the Sun will grow many times its current size, potentially engulfing the inner planets of the solar system, including Mercury and Venus, and possibly Earth. During the red giant phase, the Sun's luminosity will increase significantly. This increased luminosity will have a profound impact on the remaining inner planets. The intense heat will strip away their atmospheres, and any existing water will evaporate. Earth, if not already engulfed, will become an inhospitable, scorched world. Eventually, the Sun will reach the end of its red giant phase. The outer layers will be shed, forming a beautiful planetary nebula, a glowing shell of ionized gas that expands into space. This nebula will be visible for tens of thousands of years, providing a spectacular sight in the night sky. The remaining core of the Sun, now devoid of fuel, will contract further to become a white dwarf. This white dwarf will be composed mostly of carbon and oxygen, and will be about the size of Earth but incredibly dense. Over billions of years, the white dwarf will gradually cool and fade, eventually becoming a cold, dark remnant known as a black dwarf, a hypothetical state not yet observed. Following the red giant phase, the Sun will undergo a dramatic transformation. As it exhausts its nuclear fuel, the core's fusion processes will cease, causing the Sun to shed its outer layers. These layers will expand into space, forming a beautiful planetary nebula, a glowing shell of ionized gas that illuminates the surrounding area. This phase is relatively short-lived in astronomical terms, lasting only a few tens of thousands of years. What remains of the Sun after this shedding is its core, which will become a white dwarf. This remnant core will be composed mostly of carbon and oxygen. White dwarfs are incredibly dense objects, about the size of Earth but containing a mass comparable to that of the Sun. The Sun's white dwarf phase marks a significant reduction in its size and luminosity. These white dwarfs, despite their small size, are incredibly dense, packed with mass that causes them to remain stable against gravitational collapse due to electron degeneracy pressure. This marks a stark contrast from the Sun's earlier phases, highlighting the dramatic changes a star undergoes through its life cycle. The transition to a white dwarf will also lead to a decrease in the Sun's gravitational influence. As the outer layers are lost, the mass of the Sun decreases, causing the orbits of the remaining planets to expand. This reduction in gravitational pull will alter the dynamics of the solar system, potentially leading to changes in the orbits and stability of the planets and other objects. Planets that were once in stable orbits may find themselves drifting into more distant paths, altering the architecture of our solar system significantly. Over billions of years, the white dwarf will continue to cool and fade, gradually losing its residual heat. This cooling process is incredibly slow, as the white dwarf radiates away its energy over immense timescales. Eventually, it will become a cold, dark remnant known as a black dwarf. However, this hypothetical state, a black dwarf, is yet to be observed because the universe is not old enough for any white dwarfs to have cooled to this extent. The transition from a white dwarf to a black dwarf spans such immense timescales, on the order of many billions of years, that it remains a purely theoretical concept at this point. The orbits of planets in our solar system are not static, they evolve over time due to various gravitational interactions and perturbations. One of the key factors influencing these changes is the gravitational pull of Jupiter, the largest planet in our solar system. Jupiter's massive gravitational field exerts significant influence on the orbits of the other planets, particularly the inner planets and the asteroid belt. Jupiter's gravitational influence is so strong that it can alter the orbits of these bodies, leading to gradual shifts in their orbital parameters. As planets orbit the Sun, they experience slight gravitational tugs from other planets. These interactions cause gradual changes in their orbital parameters, such as eccentricity, how elongated the orbit is, and inclination, the tilt of the orbit relative to the plane of the solar system. Over billions of years, these gravitational perturbations can cause the orbits of the planets to become more eccentric and less circular. This means that the distance between a planet and the Sun can vary more widely over the course of its orbit, leading to changes in the planet's climate and geological processes. For example, increased eccentricity can lead to more extreme seasonal variations, affecting the planet's surface temperatures and potentially influencing atmospheric and geological activity. In addition to the gravitational influence of other planets, the Sun itself plays a crucial role in shaping the orbits of the planets. As the Sun ages, it loses mass through the emission of solar wind and the eventual shedding of its outer layers during the red giant phase. This gradual decrease in the Sun's mass reduces its gravitational pull on the planets, causing their orbits to expand over time. As a result, the planets will move further away from the Sun, leading to a more dispersed solar system. This expansion can affect the climate and stability of the planets, as they receive less solar energy, potentially leading to cooler temperatures and altered environmental conditions. Furthermore, the dynamic nature of our solar system is influenced by other factors, such as the redistribution of mass within planets due to geological activity. Events like volcanic eruptions, earthquakes, and the melting and movement of ice can shift a planet's mass, leading to subtle changes in its rotation and orbit. These internal processes can contribute to the long-term evolution of planetary orbits, adding another layer of complexity to the interactions within the solar system. The interplay of gravitational forces and internal processes shapes the architecture of the solar system, influencing the stability and habitability of planets. Understanding these orbital changes is essential for studying the past, present, and future of our planetary neighborhood. By examining the factors that influence orbital evolution, scientists can better predict the long-term stability of planetary systems and assess the potential for habitable conditions on other planets. The solar system is a complex and dynamic environment where various forces interact to influence the motion and behavior of celestial bodies. One of the key factors in these interactions is tidal friction. Tidal friction occurs when the gravitational pull of one celestial body, such as the Moon, creates tidal bulges in another body, like Earth. As the planet rotates, these tidal bulges are dragged slightly ahead of the line connecting the centers of the two bodies, creating a torque that transfers angular momentum. This process slows the rotation of the planet and causes its days to lengthen over time. Gravitational interactions also play a crucial role in shaping the orbits of celestial bodies. The gravitational pull from planets and other objects causes changes in orbital parameters, such as eccentricity, how elongated the orbit is, and inclination, the tilt of the orbit relative to the plane of the solar system. For instance, Jupiter's immense gravitational field has significant effects on the orbits of other planets and objects within the solar system, including the asteroid belt. Over long periods, these gravitational tugs can lead to gradual changes in the orbits of planets, making them more eccentric and altering their inclinations. These changes influence the overall stability and architecture of the solar system. As planets interact with each other and with the Sun, their orbits evolve, reflecting the ongoing gravitational interplay that characterizes our celestial neighborhood. The dynamic interactions within the solar system highlight the intricate and interconnected nature of gravitational forces. These forces shape the long-term stability and evolution of planetary systems, influencing everything from the length of days on Earth to the stability of orbital configurations. Understanding these interactions provides valuable insights into the past, present, and future of our solar system. Tidal friction is a fascinating phenomenon that plays a crucial role in the gradual slowing of Earth's rotation. This process is primarily driven by the gravitational interaction between Earth and the Moon. As the Moon orbits Earth, its gravitational pull creates tidal bulges in Earth's oceans. These bulges are slightly misaligned with the direct line between the centers of Earth and the Moon due to the planet's rotation. As Earth rotates, these tidal bulges are dragged slightly ahead of the Moon's position, creating a gravitational interaction that exerts a torque on Earth. This torque transfers angular momentum from Earth's rotation to the Moon's orbit. Consequently, Earth's rotation slows down, and the Moon gradually moves away from Earth at a rate of about 3.8 centimeters per year. The effect of tidal friction is subtle but cumulative. Over millions of years, this process results in a noticeable lengthening of Earth's days. For example, during the time of the dinosaurs, approximately 100 million years ago, a day on Earth was about 23 hours long. Today, a day is 24 hours long, and this gradual increase in day length continues. The continuous and subtle gravitational influences on Earth reflect the dynamic nature of our planet's relationship with the Moon. Tidal friction not only affects Earth's rotation but also plays a role in stabilizing the planet's axial tilt, which is crucial for maintaining relatively stable seasons and climate conditions over geological timescales. Overall, the effects of tidal friction on Earth's rotation exemplify the intricate and interconnected forces at play within our planetary system. Understanding these forces provides valuable insights into the long-term evolution of Earth's rotation and its impact on the planet's environment. An impact winter is a dramatic and devastating environmental change that can result from the collision of a large asteroid with Earth. When an asteroid strikes the planet, the energy released from the impact can be equivalent to millions of nuclear bombs exploding simultaneously. This tremendous energy vaporizes the asteroid and a significant portion of Earth's crust at the impact site, launching massive amounts of dust, ash, and aerosols into the atmosphere. These particles can spread globally, forming a thick layer in the stratosphere that blocks sunlight from reaching the surface. The reduction in sunlight leads to a sharp drop in global temperatures, a phenomenon known as impact winter. This cooling effect can last for months or even years, depending on the amount of debris ejected and the persistence of atmospheric particles. The disruption of sunlight profoundly affects weather patterns and agricultural productivity. Reduced temperatures can lead to shorter growing seasons, failed crops, and widespread agricultural collapse. The resulting food shortages can trigger periods of worldwide famine, as societies struggle to produce enough food to sustain their populations. This cascading effect of environmental stress can also lead to social and economic instability. A historical example of impact winter is the event that caused the extinction of the dinosaurs approximately 66 million years ago. The Chicxulub impact, which created a massive crater in what is now Mexico's Yucatan Peninsula, is believed to have launched enough debris into the atmosphere to block sunlight for an extended period. This led to a dramatic cooling of the planet, widespread wildfires, acid rain, and the collapse of ecosystems. The combination of these factors contributed to the extinction of about 75% of all species on Earth, including the non-avian dinosaurs. Impact winter highlights the vulnerability of Earth's climate and ecosystems to sudden and extreme changes caused by cosmic events. Understanding the potential consequences and developing strategies to mitigate the effects of such impacts are crucial for safeguarding our planet and ensuring the resilience of human societies and natural systems. Voyager 1, launched in 1977 as part of NASA's Voyager program, is currently the farthest human-made object from Earth. It continues to travel outward through interstellar space, having crossed the heliopause, the boundary where the Sun's solar wind is no longer strong enough to push back the interstellar medium, in 2012. This milestone marked Voyager 1's entry into interstellar space, a remarkable achievement that extends humanity's reach into the cosmos. One of the intriguing aspects of Voyager 1's journey is its predicted encounter with the star Gliese 445. In approximately 40,000 years, Voyager 1 is expected to pass within 1.5 light-years of this star, located in the constellation Camelopardalis. Gliese 445 is a red dwarf star, significantly cooler and less massive than our Sun. While this encounter will not result in any direct interaction between Voyager 1 and the star, it underscores the incredible distances and timescales involved in space exploration. The vastness of space and the immense distances between celestial objects highlight the challenges and achievements of interstellar travel. Voyager 1's journey to Gliese 445 demonstrates the incredible longevity and durability of the spacecraft, which continues to send data back to Earth despite being billions of miles away. This ongoing mission provides valuable insights into the interstellar medium and the environment beyond our solar system. Voyager 1's encounter with Gliese 445 serves as a reminder of humanity's quest for exploration and the enduring legacy of this pioneering mission. As the spacecraft continues its voyage, it carries with it a golden record, a time capsule of Earth containing sounds and images intended to communicate the story of our world to any potential extraterrestrial civilizations. Voyager 1's predicted passage by Gliese 445 in about 40,000 years highlights the extraordinary distances and timescales inherent in space exploration. This encounter exemplifies humanity's desire to reach out into the universe, seeking knowledge and understanding of the cosmos. During a geomagnetic reversal, Earth's magnetic field weakens significantly, which increases exposure to cosmic rays and solar radiation. The magnetic field normally acts as a protective shield, deflecting charged particles from the Sun and cosmic rays from space. When this field weakens, more of these high-energy particles can penetrate the atmosphere and reach the surface. This increased exposure to radiation can have several biological and technological impacts. On the technological side, increased radiation can interfere with the functioning of satellites and other space-based technology. High-energy particles can damage electronic components, leading to malfunctions or failures in satellites. This can disrupt communication, navigation, and other satellite-dependent services. Satellites in orbit are particularly vulnerable during periods of weak magnetic fields, as they lack the protective buffer provided by a stronger magnetic field. Solar storms, which are more frequent and intense during geomagnetic reversals, can exacerbate this problem by increasing the flux of charged particles that satellites encounter. The increased exposure to solar radiation can also affect power grids on Earth. Geomagnetic storms, which can be more frequent during periods of weak magnetic fields, can induce currents in power lines, leading to voltage instabilities and potentially causing blackouts. These geomagnetically induced currents, GICs, can overload power transformers and other critical infrastructure, leading to widespread outages and damage to the electrical grid. The economic impact of such disruptions can be significant, affecting industries, businesses, and daily life. The 1989 Quebec blackout, caused by a geomagnetic storm, is a notable example of how powerful these events can be. Geomagnetic reversals are natural occurrences that have happened numerous times throughout Earth's history. During a reversal, the magnetic field's polarity flips, which can take thousands of years to complete. The last reversal, known as the Brune-Matsuyama reversal, occurred about 780,000 years ago. While the exact timing and frequency of these reversals are not entirely predictable, geological records indicate that they happen on average every several 100,000 years. Understanding the potential impacts of geomagnetic reversals is crucial for developing strategies to mitigate their effects on both biological systems and modern technology. Research into past geomagnetic reversals, combined with current technological advancements, can help scientists anticipate and prepare for the challenges associated with these events. One approach to mitigating the biological impacts of increased radiation is improving medical monitoring and treatment for radiation exposure. Advances in medical technology and genetic research could lead to better detection of radiation-induced damage and more effective therapies for mitigating its effects. Protective measures, such as enhanced radiation shielding in habitats and vehicles for astronauts, could also help reduce the risk during space missions. For technological systems, improving the resilience of satellites and power grids is essential. This includes hardening electronic components to withstand higher radiation levels and developing more robust backup systems to maintain critical functions during solar storms. For example, engineers can design satellites with radiation-hardened electronics and redundancy to ensure continued operation during geomagnetic storms. Similarly, power grids can be equipped with surge protectors and other technologies to mitigate the effects of GICs. Early warning systems play a crucial role in protecting technological infrastructure. Space weather monitoring programs, such as those run by NASA, the European Space Agency, track solar activity and provide forecasts of potential geomagnetic storms. These forecasts allow operators of satellites and power grids to take preventive measures, such as temporarily shutting down vulnerable systems or adjusting operational parameters to reduce risk. International collaboration is also vital for addressing the challenges posed by geomagnetic reversals. Sharing data, research findings, and best practices among countries can enhance global preparedness and response capabilities. Joint efforts in space weather monitoring, satellite technology, and power grid protection can lead to more effective mitigation strategies and a better understanding of the complex interactions between Earth's magnetic field and solar radiation. Many species, such as birds, marine turtles, and certain fish, rely on Earth's magnetic field to navigate during their long migrations. These animals possess a sense known as magnetoreception, which allows them to detect and respond to the magnetic field, helping them travel vast distances with remarkable accuracy. During a geomagnetic reversal, the magnetic field weakens and its structure becomes more complex and unstable, potentially causing significant disruptions in these migratory patterns. When the magnetic field flips, the poles switch places, and the field can weaken to as little as 10% of its usual strength. This altered state can create confusion for animals that depend on the magnetic field for orientation. For instance, migratory birds that travel thousands of miles between breeding and wintering grounds could find their internal compasses misaligned, leading to disorientation and difficulty finding their usual routes. Marine turtles, which use the magnetic field to navigate across oceans to their nesting sites, could also be affected. Disrupted navigation might cause them to stray off course, potentially leading to lower reproductive success as they may not reach their intended nesting beaches. Such disruptions can have cascading effects on ecological systems, as the timing and success of migrations are crucial for maintaining the balance of ecosystems. The impact of these changes will not be uniform across all species. Some may adapt to the temporary disarray, while others could face significant challenges. The overall effect on ecological systems would depend on the duration of the magnetic field instability and the adaptability of the affected species. Understanding how geomagnetic reversals influence migratory patterns is crucial for predicting and mitigating the potential ecological impacts. Continued research in this area can help us develop strategies to support vulnerable species during periods of magnetic field instability. Solar storms, also known as space weather events, occur when the Sun emits bursts of energy in the form of solar flares and coronal mass ejections, CMEs. These events release a significant amount of charged particles and radiation into space, which can have profound effects on Earth's technology and infrastructure. Solar flares are intense bursts of radiation caused by the release of magnetic energy on the Sun's surface. They emit a broad spectrum of radiation, including X-rays and ultraviolet light, which can affect the Earth's ionosphere and disrupt high-frequency radio communications. Coronal mass ejections, on the other hand, are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. When these CMEs hit the Earth's magnetosphere, they can cause geomagnetic storms that disturb Earth's magnetic field. One of the primary technological impacts of increased solar activity is the potential damage to satellites. Satellites are exposed to high levels of radiation during solar storms, which can interfere with their electronic circuits and systems. This interference can lead to malfunctions or even complete failure of the satellites. Communication and navigation systems that rely on satellites, such as GPS services, satellite-based internet, and television, can be disrupted. For instance, the radiation can cause the charging of satellite components, leading to discharges that disrupt operations. The increased density of charged particles in the Earth's outer atmosphere can also increase drag on satellites, potentially altering their orbits. Power grids on Earth are particularly vulnerable to the effects of solar storms. The influx of charged particles from a solar storm can induce electric currents in power lines, transformers, and other components of the electrical grid. This can result in voltage surges, equipment damage, and widespread power outages. A notable example of such an event is the 1989 Quebec blackout, caused by a geomagnetic storm triggered by a solar flare. The storm induced currents that overwhelmed Quebec's power grid, leaving millions without electricity for hours. Power grid failures due to solar storms can have cascading effects, disrupting water supply systems, emergency services, and other critical infrastructure. During periods of weakened magnetic fields, such as those associated with geomagnetic reversals, the effects of solar storms can be even more pronounced. The Earth's magnetic field acts as a protective shield, deflecting charged particles from the Sun and cosmic rays from space. When this field weakens, more of these high-energy particles can penetrate the atmosphere and reach the surface. The reduced strength of Earth's magnetic shield during a geomagnetic reversal allows more solar radiation to penetrate the atmosphere, increasing the risk of technological disruptions. The enhanced solar radiation during these periods can pose significant challenges for maintaining and protecting technological systems. The increased radiation can interfere with the functioning of satellites and other space-based technology, leading to malfunctions or failures. High-energy particles can damage electronic components, disrupt communication and navigation systems, and increase the drag on satellites in low Earth orbit. These disruptions can have significant economic and societal impacts, affecting industries, transportation, and daily life. The potential impacts of solar storms on power grids are also heightened during periods of weakened magnetic fields. Geomagnetic storms can induce currents in power lines and transformers, leading to voltage instabilities and potentially causing blackouts. The induced currents can damage transformers, which are critical components of the power grid, leading to long-term outages and expensive repairs. The risk of power grid failures during solar storms underscores the importance of monitoring and preparing for space weather events. Overall, the impact of solar storms on technology highlights the importance of monitoring and preparing for space weather events. Efforts to forecast solar activity, develop resilient infrastructure, and create protective measures are crucial for mitigating the potential damage caused by these powerful natural phenomena. Space weather monitoring programs, such as those run by NASA and the European Space Agency, track solar activity and provide forecasts of potential geomagnetic storms. These forecasts allow operators of satellites and power grids to take preventive measures, such as temporarily shutting down vulnerable systems or adjusting operational parameters to reduce risk. Developing resilient infrastructure is also essential for mitigating the impacts of solar storms. For satellites, this can include designing radiation-hardened electronics and incorporating redundancy to ensure continued operation during solar storms. For power grids, this can involve installing surge protectors, ground wires, and other technologies to mitigate the effects of geomagnetically induced currents. Building resilience into critical infrastructure helps to minimize disruptions and ensure the continuity of essential services during space weather events. During a geomagnetic reversal, Earth's magnetic field weakens and becomes more unstable, leading to increased geomagnetic activity. This heightened activity can induce electric currents in power lines and other components of the electrical grid, potentially causing significant disruptions and even blackouts. These induced currents, known as geomagnetically induced currents, GICs, can overload transformers and other critical infrastructure within the grid. This overloading can result in equipment damage, voltage instability, and power outages. To mitigate these risks, infrastructure might require adaptation to withstand the increased geomagnetic stress. This can include the implementation of better monitoring systems to detect geomagnetic activity, the use of protective devices such as surge protectors, and the reinforcement of critical grid components to handle higher current loads. Improving the resilience of power grids to geomagnetic disturbances is essential for maintaining reliable electrical supply during periods of heightened geomagnetic activity. Understanding and preparing for the effects of geomagnetic reversals on electrical grids is crucial for ensuring the stability and functionality of modern technological infrastructure. Massive stars, those with at least 8 times the mass of our Sun, experience life cycles that are both dramatic and vital to the cosmos. These stars burn through their nuclear fuel at an astonishing rate, undergoing nuclear fusion to produce heavier elements in their cores. The process begins with the fusion of hydrogen into helium, a stage known as the main sequence phase. As the hydrogen in the core is exhausted, the star evolves, burning progressively heavier elements such as helium, carbon, oxygen, and so on, up to iron. The creation of iron in the core marks a critical point in the life cycle of a massive star. Iron fusion does not release energy, instead, it consumes energy. This leads to a collapse of the core under gravity, as the outward pressure from fusion that has been counteracting gravity diminishes. The core collapse happens incredibly fast, in a fraction of a second, and results in a catastrophic explosion known as a supernova. The supernova explosion is an incredibly energetic event, releasing more energy in a few seconds than the Sun will emit over its entire lifetime. This explosion disperses the outer layers of the star into space, spewing out the heavier elements created during the star's life into the interstellar medium. These elements, such as carbon, oxygen, and iron, are crucial for the formation of new stars, planets, and even life itself. The core that remains after the supernova can become either a neutron star or, if the original star was massive enough, collapse further into a black hole. Neutron stars are incredibly dense, with a mass comparable to that of the Sun but compressed into a sphere only about 20 kilometers in diameter. If the core's mass exceeds about 3 times that of the Sun, the gravitational pull is so strong that not even light can escape, resulting in a black hole. The life cycle of massive stars thus plays a fundamental role in the ongoing creation and evolution of the cosmos. By producing and distributing heavy elements, these stars contribute to the chemical enrichment of the universe, paving the way for new generations of stars and planetary systems. This continuous cycle of star birth and death is essential for the dynamic and ever-changing nature of the universe. Nucleosynthesis in supernova explosions is a critical process that contributes to the formation of elements heavier than iron, playing a key role in the cosmic cycle of matter. During the lifetime of a massive star, nuclear fusion in its core creates elements up to iron. However, the fusion of iron absorbs energy rather than releasing it, leading to the collapse of the star's core under gravity. When a massive star undergoes a supernova explosion, the extreme temperatures and pressures generated in the core collapse provide the conditions necessary for nucleosynthesis of heavier elements. This process involves rapid neutron capture, known as the UR process, where neutrons are captured by atomic nuclei before they can decay. This rapid addition of neutrons creates highly unstable, neutron-rich isotopes that eventually decay into stable forms of heavy elements, such as gold, platinum, and uranium. The supernova explosion disperses these newly formed elements into the interstellar medium, enriching it with a variety of heavy elements. These enriched materials become part of the gas and dust clouds that will eventually coalesce to form new stars and planetary systems. In this way, supernova nucleosynthesis contributes to the ongoing creation and evolution of the cosmos, providing the building blocks for future generations of stars, planets, and potentially life itself. Understanding nucleosynthesis in supernovae offers valuable insights into the origin of elements in the universe, and the processes that drive stellar evolution. It highlights the interconnectedness of cosmic phenomena, and the dynamic nature of the universe, where the death of one star can seed the birth of new celestial bodies. Saturn, often recognized for its stunning and iconic ring system, is expected to undergo significant visual changes over the next 100 to 300 million years, as its rings gradually disappear. This transformation will not only alter Saturn's appearance but also impact its atmospheric dynamics and albedo, the measure of the planet's reflectivity. The process driving the disappearance of Saturn's rings is known as ring rain. This phenomenon occurs when particles from the rings are pulled into Saturn's atmosphere by its gravitational forces. These particles, composed mainly of water ice with traces of rocky material, gradually spiral inward, influenced by Saturn's magnetosphere, and the gravitational pull from the planet itself. As these particles enter the atmosphere, they evaporate and disperse, causing the rings to deplete over time. As the rings dissipate, Saturn's visual characteristics will change dramatically. The bright, reflective rings that have defined Saturn's appearance for centuries will fade, leaving a planet that looks more like the other gas giants in our solar system, such as Jupiter, Uranus, and Neptune. Without its rings, Saturn will lose much of its distinctiveness, appearing as a more uniform, cloud-covered sphere. This transformation will mark a significant shift in how we perceive one of the most recognizable planets in our solar system. The disappearance of the rings will also impact Saturn's albedo. The rings are highly reflective, contributing significantly to Saturn's overall brightness when viewed from space. They reflect sunlight, enhancing Saturn's visibility and giving it a striking appearance. As the rings vanish, Saturn's albedo will decrease, causing the planet to appear dimmer. This reduction in reflectivity will alter how Saturn is observed from Earth and space telescopes, changing its prominence in the night sky. Moreover, the rings play a crucial role in Saturn's atmospheric dynamics by influencing temperature and weather patterns. The rings create shadows on Saturn's surface, leading to temperature variations that affect atmospheric circulation. These temperature differences drive wind patterns and weather systems unique to Saturn. With the rings gone, these dynamics will change, potentially altering wind patterns and weather systems on the planet. The absence of ring shadows could lead to more uniform temperatures across Saturn's surface, affecting atmospheric movement and potentially stabilizing or changing existing weather phenomena. The loss of Saturn's rings may also have broader implications for our understanding of ring systems around other planets and celestial bodies. Observing the gradual disappearance of Saturn's rings provides a natural laboratory to study the processes affecting ring dynamics, particle interactions, and the long-term evolution of ring systems. These observations can offer insights into similar phenomena around other gas giants, both within our solar system and in exoplanetary systems. Saturn's rings have long fascinated astronomers and the general public alike. Their intricate structure, composed of countless individual particles ranging in size from tiny grains to large boulders, showcases the complexity and beauty of our solar system. The gradual loss of these rings underscores the dynamic and ever-changing nature of celestial bodies, reminding us that even the most iconic features are not permanent. The process of ring rain and the eventual disappearance of Saturn's rings also highlight the intricate interplay between gravitational forces, magnetic fields, and planetary atmospheres. Understanding these interactions helps scientists develop more accurate models of planetary systems and predict their long-term evolution. The study of Saturn's rings and their gradual loss can inform our knowledge of similar processes occurring around other planets and moons, enhancing our comprehension of the broader cosmos. Jupiter, the largest planet in our solar system, wields a massive gravitational field that significantly influences the orbits and dynamics of other celestial bodies. Its gravitational pull is strong enough to affect the trajectories of not only its numerous moons but also other planets, asteroids, and comets. This influence extends far beyond Jupiter's immediate vicinity, shaping the overall architecture and stability of the solar system. One of the most notable effects of Jupiter's gravitational influence is on the asteroid belt located between Mars and Jupiter. Jupiter's gravity creates gaps in the asteroid belt known as Kirkwood gaps. These gaps are areas where the gravitational perturbations from Jupiter create unstable orbits, causing asteroids to be either ejected from the belt or moved to different regions. The result is a pattern of gaps at specific distances from the Sun, corresponding to orbital resonances with Jupiter. These gravitational interactions play a crucial role in maintaining the structure of the asteroid belt, preventing it from becoming more densely populated. Additionally, Jupiter's gravitational interactions can capture passing comets, pulling them into stable orbits around the planet or altering their paths through the solar system. Some comets, known as Jupiter family comets, have their orbits influenced or controlled by the giant planet. These comets typically have short orbital periods and are confined to regions closer to the Sun. Jupiter's ability to capture and influence comets not only affects their orbits but also impacts the likelihood of these objects entering the inner solar system, and potentially posing a threat to Earth. Jupiter's immense mass also plays a crucial role in shaping the overall architecture of the solar system. Its gravitational interactions can cause changes in the orbital eccentricity, how elongated an orbit is, and inclination, the tilt of an orbit relative to the plane of the solar system, of other planets. These interactions can lead to the long-term stabilization of planetary orbits, ensuring that the planets remain in relatively stable and predictable paths around the Sun. This gravitational influence helps maintain the spacing and alignment of the planets, contributing to the overall stability of the solar system over billions of years. Furthermore, Jupiter acts as a kind of cosmic shield for the inner planets, including Earth. Its strong gravitational field can deflect or capture potentially hazardous comets and asteroids that might otherwise pose a threat to the inner solar system. By diverting these objects, Jupiter reduces the likelihood of catastrophic impacts on Earth and other inner planets. This protective role is significant, as the impact of a large asteroid or comet could have devastating consequences for life on Earth, similar to the event that caused the extinction of the dinosaurs approximately 66 million years ago. Jupiter's gravitational influence extends beyond the asteroid belt and inner solar system. Its interactions with other gas giants, such as Saturn, Uranus, and Neptune, contribute to the complex gravitational dynamics of the outer solar system. These interactions can affect the orbits of distant objects in the Kuiper belt and Oort cloud, regions populated by small icy bodies and potential comets. The gravitational interplay between Jupiter and these outer solar system objects can result in the ejection of some bodies into interstellar space or their redirection into the inner solar system. The study of Jupiter's gravitational influence is essential for understanding the long-term evolution and stability of the solar system. By analyzing the effects of Jupiter's gravity on the orbits of asteroids, comets, and other planets, scientists can gain insights into the processes that have shaped the solar system over billions of years. This research also helps predict the future dynamics of the solar system and assess potential threats from near-Earth objects. Jupiter's role as a gravitational giant and cosmic shield highlights the interconnected nature of the solar system. The planet's immense mass and gravitational influence affect a wide range of celestial bodies, from tiny asteroids to distant comets, shaping their orbits and interactions. Understanding these gravitational dynamics is crucial for developing accurate models of the solar system's evolution and assessing the potential risks and benefits of Jupiter's influence. In addition to its gravitational effects, Jupiter's magnetic field also plays a significant role in the solar system. Jupiter has the most powerful magnetic field of any planet, extending far into space and creating a region known as the magnetosphere. This magnetic field interacts with the solar wind, protecting Jupiter's moons from some of the harmful effects of solar radiation. The study of Jupiter's magnetosphere provides valuable insights into planetary magnetic fields and their interactions with the surrounding space environment. The formation of planetary rings in the solar system is an intriguing process influenced by tidal forces and collisions. Saturn's rings are perhaps the most famous example, showcasing a bright and expansive system composed primarily of ice and rock particles. These rings are believed to have formed from the remnants of a moon or comet that was torn apart by Saturn's strong gravitational forces. Tidal forces play a crucial role in ring formation. When a celestial body, such as a moon or comet, ventures too close to a planet, the planet's gravity can exceed the body's own gravitational cohesion, causing it to break apart. This process, known as the Roche limit, leads to the creation of rings from the resulting debris. The particles that make up the rings are kept in place by the planet's gravity and the balance between centrifugal and centripetal forces. Another example of potential ring formation involves Mars and its moon Phobos. Phobos is gradually spiraling inward toward Mars and is expected to reach the Roche limit in about 30 to 50 million years. When this happens, tidal forces will tear Phobos apart, creating a ring system around Mars. Although the resulting rings would not be as extensive as Saturn's, they would still be a remarkable spectacle and provide valuable insights into the dynamics of planetary rings. The formation and evolution of planetary rings highlight the dynamic nature of the solar system and the powerful gravitational interactions that shape celestial bodies. Rings can serve as both a testament to past cosmic events and a laboratory for studying planetary processes. Tidal forces, which arise from gravitational interactions between celestial bodies, play a crucial role in shaping the internal dynamics, geological activity, and rotational characteristics of planets and moons. These forces result from the differential gravitational pull exerted by a larger body, such as a planet or star, on different parts of a smaller body, like a moon or satellite. One of the most well-known examples of tidal forces at work is the interaction between Earth and the Moon. The Moon's gravitational pull creates tidal bulges in Earth's oceans, leading to the phenomenon of tides. Over long periods, these tidal interactions have also affected Earth's rotation, gradually slowing it down and lengthening the length of a day. Similarly, the Moon's rotation has been synchronized to always show the same face to Earth, a state known as tidal locking. Tidal forces are significant in influencing geological activity. For instance, Jupiter's moon Io experiences intense tidal forces due to its close proximity to the gas giant and the gravitational interactions with Jupiter and other moons. These tidal forces generate significant internal friction and heat, driving extensive volcanic activity on Io's surface, making it the most volcanically active body in the solar system. On a larger scale, tidal forces can also shape the long-term stability and evolution of planetary bodies. For example, the tidal interactions between Saturn and its moon, Enceladus, are believed to drive the subsurface ocean beneath Enceladus's icy crust. The friction generated by tidal forces helps maintain liquid water, which has implications for the moon's potential habitability and geological activity. Tidal forces can also influence the formation and evolution of planetary rings. As mentioned earlier, when moons or other celestial bodies come too close to a planet, they can be torn apart by tidal forces, resulting in the formation of rings. This process highlights the dynamic nature of tidal interactions in shaping the appearance and structure of planetary systems. Overall, tidal forces are a fundamental aspect of planetary evolution, influencing everything from rotational dynamics to geological activity and the formation of rings. Understanding these interactions provides valuable insights into the complex and interconnected nature of celestial bodies within our solar system and beyond. Earth's long-term climate patterns are significantly influenced by changes in its orbital characteristics, such as orbital eccentricity and axial tilt. These variations, known as Milankovitch cycles, play a crucial role in driving shifts in climate, including the onset and retreat of ice ages. Orbital eccentricity refers to the shape of Earth's orbit around the Sun, which can range from more circular to more elliptical. When the orbit is more elliptical, the difference between the closest, perihelion, and farthest, aphelion, points from the Sun is greater, leading to more pronounced seasonal variations. This change in orbital shape occurs over a cycle of about 100,000 years and influences the distribution of solar radiation received by Earth, affecting long-term climate trends. Axial tilt, or obliquity, is the angle between Earth's rotational axis and its orbital plane. This tilt varies over a cycle of approximately 41,000 years, and affects the severity of the seasons. Greater axial tilt increases the contrast between summer and winter, leading to more extreme seasonal climates. Conversely, a smaller tilt results in milder seasons. These changes in obliquity can impact the distribution of sunlight across the planet, contributing to shifts in climate patterns. Another important factor is precession, the wobble in Earth's rotational axis, which occurs over a cycle of about 26,000 years. Precession alters the timing of the seasons in relation to Earth's position in its orbit, affecting the distribution of solar energy and contributing to long-term climate variability. The combined effects of these orbital variations influence the amount and distribution of solar radiation received by Earth, driving changes in climate over tens of thousands to hundreds of thousands of years. For example, periods of low eccentricity and reduced axial tilt can lead to cooler global temperatures, promoting the growth of ice sheets and glaciers. Conversely, higher eccentricity and greater axial tilt can result in warmer periods, leading to the retreat of ice sheets. Understanding the role of orbital shifts in climate change helps scientists reconstruct past climates and predict future climate trends. These insights are crucial for understanding the natural forces that shape Earth's climate, and for developing strategies to address the ongoing challenges of climate change. Earth has experienced several mass extinction events, which are periods in its history when a significant percentage of the planet's species went extinct in a relatively short period of time. These catastrophic events have been caused by various factors, including asteroid impacts, volcanic activity, and dramatic changes in climate. Studying these events helps scientists understand the potential threats that could lead to future extinctions and informs strategies to mitigate their impacts. One of the most famous mass extinction events is the Cretaceous-Paleogene (KPG) extinction event, which occurred about 66 million years ago. It is widely believed that this event was caused by a massive asteroid impact that created the Chicxulub crater in what is now Mexico. The impact would have triggered widespread wildfires, a nuclear winter effect from dust and aerosols blocking sunlight, and other environmental disruptions, leading to the extinction of about 75% of Earth's species, including the non-avian dinosaurs. Another significant mass extinction event is the Permian-Triassic extinction event, which occurred around 252 million years ago. This event, also known as the Great Dying, is considered the most severe extinction event in Earth's history, wiping out approximately 90 to 96% of all marine species and 70% of terrestrial vertebrate species. The causes of this event are thought to include massive volcanic eruptions in the Siberian Traps, leading to climate change, ocean acidification, and anoxia, lack of oxygen. The study of these and other mass extinction events, such as the Ordovician-Silurian, and the Triassic-Jurassic extinctions, provides valuable insights into the mechanisms driving large-scale biodiversity loss. By understanding the triggers and consequences of past extinctions, scientists can better assess the risks posed by current and future threats, such as climate change, habitat destruction, and potential asteroid impacts. This knowledge is crucial for developing strategies to protect biodiversity and mitigate the impacts of potential extinction-causing events. Space weather, primarily driven by solar activity, poses significant risks to satellites and space technology. Solar storms, including solar flares and coronal mass ejections, CMEs, release bursts of electromagnetic radiation and energetic particles that can disrupt satellite operations and damage electronic components. One key risk is radiation exposure. High-energy particles from solar storms can penetrate satellite surfaces, causing damage to electronic circuits and components. This can lead to malfunctions or complete failure of satellite systems. Additionally, increased solar activity heats and expands Earth's upper atmosphere, increasing drag on low Earth orbit satellites. This can cause satellites to lose altitude and potentially re-enter the atmosphere prematurely. Geomagnetic storms, caused by CMEs interacting with Earth's magnetic field, can induce electric currents in satellites, leading to further damage and operational disruptions. To mitigate these risks, several strategies can be employed. Satellites can be equipped with radiation-hardened components and additional shielding to protect against high-energy particles. Adjusting satellite orbits to minimize exposure to harmful radiation and atmospheric drag can help prolong their operational lifetimes. Space weather monitoring and forecasting systems can provide advance warnings of solar storms, allowing operators to take preventive measures, such as powering down sensitive electronics or adjusting satellite orientations. Incorporating redundant systems and designing satellites to withstand space weather effects can enhance their resilience and reliability. By implementing these strategies, we can better protect critical space infrastructure and ensure the continued functionality of satellites and other space-based technologies. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions are just right to support liquid water on the surface of a planet. This is a key factor in the potential for life as we know it, since liquid water is essential for biological processes. The habitable zone's location is primarily determined by the star's luminosity, which dictates the amount of heat and light the star emits. Changes in stellar luminosity can significantly influence the location and stability of habitable zones. For instance, as a star ages, its luminosity typically increases, causing the habitable zone to move outward. This means that a planet that is currently within the habitable zone might find itself too close to the star, becoming too hot for liquid water to exist. Conversely, planets that are currently outside the habitable zone could eventually enter it as the star brightens over time. Planetary orbits also play a crucial role in determining habitability. Eccentric orbits, which vary significantly in distance from the star during the planet's revolution, can lead to extreme variations in temperature. This can make it challenging for stable, life-supporting conditions to persist. More circular orbits, which maintain a relatively constant distance from the star, are more conducive to stable climates that can support life. The study of habitable zones is not limited to our own solar system. Exoplanet research, aided by telescopes like the Kepler Space Telescope, has identified numerous planets within the habitable zones of their parent stars. However, being in the habitable zone is just one of many factors that determine a planet's potential to support life. Other factors include the planet's atmosphere, magnetic field, geological activity, and the presence of water and other essential chemicals. Understanding how habitable zones shift over time helps astronomers identify potential planets that could harbor life and sheds light on the long-term habitability of planets, including Earth. Increased cosmic ray exposure has the potential to significantly affect Earth's atmospheric chemistry and climate. Cosmic rays, which are high-energy particles originating from outer space, can penetrate the atmosphere and interact with its molecules, leading to various chemical reactions. These interactions can result in the production of secondary particles and ions, which can influence cloud formation and, consequently, weather and climate patterns. During geomagnetic reversals, when Earth's magnetic field weakens, the planet becomes more exposed to cosmic rays. The magnetic field normally acts as a shield, deflecting many of these high-energy particles. However, a weakened magnetic field means that more cosmic rays can penetrate the atmosphere and reach Earth's surface. This increased exposure can lead to a higher incidence of radiation, affecting both the environment and living organisms. The potential impacts of increased cosmic ray exposure during geomagnetic reversals include changes in the ionization levels of the atmosphere, which can affect cloud nucleation processes. This could lead to alterations in cloud cover and precipitation patterns, potentially influencing global climate. Additionally, increased radiation reaching Earth's surface poses risks to human health, as well as to technological infrastructure, such as satellites and power grids. Understanding the effects of cosmic rays on Earth's atmosphere and climate is essential for assessing the broader implications of geomagnetic reversals and other space weather events. Continued research in this area helps us better prepare for and mitigate the potential impacts of increased cosmic ray exposure. The existence of subsurface oceans in icy moons is one of the most exciting and intriguing areas of study in planetary science and astrobiology. Tidal heating, caused by the gravitational interaction between a moon and its parent planet, can generate sufficient heat to maintain liquid water beneath a moon's icy crust. This process is well exemplified by Jupiter's moon Europa, which is believed to have a subsurface ocean beneath its thick ice shell. Europa experiences strong tidal forces due to its proximity to Jupiter and the gravitational pull from other nearby moons, such as Io and Ganymede. These tidal forces cause Europa's interior to flex and generate frictional heat, preventing the water beneath its icy crust from freezing solid. The presence of a global subsurface ocean on Europa makes it one of the prime targets for astrobiological studies, as liquid water is a key ingredient for life as we know it. The potential for subsurface oceans to harbor life extends beyond Europa. Saturn's moon Enceladus, for instance, also shows evidence of a subsurface ocean. Observations from the Cassini spacecraft revealed plumes of water vapor and ice particles erupting from Enceladus's south polar region, indicating active hydrothermal processes beneath its ice crust. These hydrothermal vents could provide the necessary conditions for life, similar to the hydrothermal vents found on Earth's ocean floors. The study of subsurface oceans in icy moons opens up new possibilities for understanding the habitability of these distant worlds. Future missions, such as NASA's Europa Clipper and the European Space Agency's JUICE, Jupiter Icy Moons Explorer, aim to further explore these intriguing environments and search for signs of life. The presence of subsurface oceans in icy moons, sustained by tidal heating, offers a fascinating opportunity for astrobiological research. These hidden oceans could potentially harbor life, making them key targets for future exploration and study. Galactic interactions and mergers are dynamic processes that can dramatically reshape the structures of galaxies and trigger significant star formation. When galaxies interact, their gravitational forces distort each other's shapes, leading to the formation of tidal tails, bridges, and other intricate structures. These interactions can compress gas clouds within the galaxies, igniting bursts of star formation as the gas collapses under gravity to form new stars. One of the most anticipated galactic interactions is the impending collision between the Milky Way and the Andromeda Galaxy. Currently, Andromeda is on a collision course with the Milky Way, and this cosmic event is expected to occur in about 4.5 billion years. As the two galaxies approach each other, their mutual gravitational pull will cause them to distort and merge over a span of several billion years. The study of galactic interactions and mergers provides valuable insights into the evolution of galaxies and the dynamic processes that shape the universe. By observing other interacting galaxies, astronomers can better understand the mechanisms driving star formation and galactic evolution. White dwarfs represent the final stage of stellar evolution for Sun-like stars. After a star like our Sun exhausts its nuclear fuel, it sheds its outer layers and leaves behind a hot, dense core known as a white dwarf. Initially, these white dwarfs are incredibly hot, with surface temperatures exceeding 100,000 degrees Celsius. Over billions of years, white dwarfs will gradually cool as they radiate away their residual heat into space. This cooling process occurs at an extremely slow rate due to their high density and small size. As the white dwarf cools, its luminosity decreases, and it dims progressively. Eventually, after tens to hundreds of billions of years, a white dwarf will cool to the point where it no longer emits significant heat or light. At this stage, it becomes a black dwarf. However, because the universe is only about 13.8 billion years old, no black dwarfs are expected to exist yet, as there hasn't been enough time for any white dwarfs to cool completely to this state. The cooling and transformation of white dwarfs into black dwarfs illustrate the ultimate fate of many stars in our galaxy, including our Sun. This process highlights the long-term evolution of stellar remnants and their role in the broader cosmic cycle. Nebulae play a crucial role in the process of star formation by enriching the interstellar medium with essential elements and serving as stellar nurseries. One of the most fascinating types of nebulae involved in this process is the planetary nebula. Despite their name, planetary nebulae have nothing to do with planets, rather, they are formed from the outer layers of dying stars. As stars like our Sun approach the end of their life cycles, they shed their outer layers into space, creating beautiful, glowing clouds of gas and dust. These planetary nebulae are rich in elements such as hydrogen, helium, carbon, oxygen, and nitrogen, which are essential for the creation of new stars and planetary systems. When stars exhaust their nuclear fuel, they go through a series of stages that culminate in the shedding of their outer layers. For Sun-like stars, this process begins with the red giant phase, where the star expands and becomes cooler. Eventually, the outer layers are expelled, forming a planetary nebula, while the core of the star collapses into a white dwarf. The expelled material is ionized by the intense radiation from the hot core, causing the nebula to glow brightly. This glowing shell of gas and dust is what we observe as a planetary nebula. When these elements are released into the interstellar medium, they mix with the existing gas and dust, increasing the overall abundance of materials necessary for the formation of new stars and planetary systems. The presence of these heavier elements, also known as metals in astronomical terms, is crucial for the development of rocky planets and the complex chemistry required for life. Without the continuous recycling of elements through processes like those that create planetary nebulae, the universe would lack the diversity of materials needed to form complex structures. Star formation typically occurs within giant molecular clouds, also known as stellar nurseries. These vast clouds of gas and dust can be several light-years across and contain enough material to form thousands of stars. The process of star formation begins when a region within a molecular cloud collapses under its own gravity, forming a dense core known as a protostar. As the protostar continues to collapse and heat up, nuclear fusion ignites in its core, marking the birth of a new star. The formation of a star from a molecular cloud is a complex process influenced by various factors, including turbulence within the cloud, magnetic fields, and the presence of nearby massive stars that can trigger the collapse of the cloud through their radiation and stellar winds. The remnants of the surrounding gas and dust that do not collapse into the star can coalesce to form planets, moons, asteroids, and other celestial bodies, creating a new solar system. The cycle of star birth, life, and death, with nebulae serving as intermediaries, is a fundamental aspect of cosmic evolution. This process ensures the continuous creation and recycling of elements, contributing to the dynamic and ever-changing nature of the universe. As stars go through their life cycles, they process and redistribute the elements, enriching the interstellar medium, and providing the raw materials for future generations of stars and planets. Supernovae, the explosive deaths of massive stars, also play a critical role in this cycle. When a massive star explodes as a supernova, it releases an enormous amount of energy, and expels its outer layers into space. These layers contain heavy elements that were formed during the star's lifetime through nuclear fusion and during the supernova explosion itself. The resulting supernova remnant enriches the surrounding interstellar medium with these elements, contributing to the chemical diversity of the galaxy. The study of nebulae and their role in star formation provides valuable insights into the origins and evolution of stars, planets, and the building blocks of life. By observing nebulae in various stages of development, astronomers can learn about the processes that govern the birth and death of stars. For example, the famous Orion Nebula, a region of active star formation, offers a glimpse into the early stages of star and planetary system formation. Observations of planetary nebulae, on the other hand, provide insights into the final stages of stellar evolution and the recycling of elements into the interstellar medium. Advancements in telescopic technology have allowed astronomers to study nebulae in greater detail than ever before. Instruments like the Hubble Space Telescope have captured stunning images of nebulae, revealing their intricate structures and helping scientists understand the physical processes at work. These observations have led to significant discoveries, such as the identification of protoplanetary disks around young stars, which are the birthplaces of new planets. Planetary albedo, or the measure of how much sunlight a planet reflects, can be significantly affected by changes such as the loss of rings or alterations in atmospheric composition. The albedo of a planet influences its temperature and climate, as it determines the amount of solar energy absorbed versus reflected back into space. For example, Saturn's rings are highly reflective and contribute to its overall brightness. If Saturn were to lose its rings, its albedo would decrease, making the planet appear dimmer. This reduction in reflectivity would allow more solar energy to be absorbed by the planet, potentially leading to changes in its atmospheric and surface temperatures. Similarly, changes in a planet's atmosphere can also impact its albedo. The composition, thickness, and cloud cover of the atmosphere play significant roles in determining how much sunlight is reflected. For instance, an increase in cloud cover can enhance a planet's albedo by reflecting more sunlight, while a decrease in cloud cover or the presence of darker, more absorbing atmospheric particles can reduce it. Understanding how changes in planetary albedo affect climate and temperature is essential for studying the evolution and habitability of planets. It also provides insights into the dynamics of planetary systems and the various factors that influence their appearance and environmental conditions. The evolution of stars profoundly impacts the planetary systems that orbit them. As stars age, their luminosity and gravitational influence undergo significant changes, which can alter the conditions for life on any orbiting planets. One of the most critical aspects of this evolution is the shifting of the habitable zone, the region around a star where conditions are suitable for liquid water to exist. During a star's main sequence phase, it steadily burns hydrogen in its core, maintaining a relatively stable output of energy. However, as the star exhausts its hydrogen supply and begins to burn heavier elements, its luminosity increases. For stars like our Sun, this transition marks the start of the red giant phase, where the star expands and becomes much brighter. As a result, the habitable zone moves outward. Planets that were once within this zone might become too hot, leading to the loss of any existing liquid water. Conversely, planets that were previously too cold might enter the habitable zone, potentially creating conditions favorable for life. The gravitational influence of a star also changes as it evolves. For instance, when a star enters the red giant phase, it loses mass through stellar winds. This mass loss reduces the star's gravitational pull, causing the orbits of its planets to expand. Such changes can lead to increased orbital instability, potentially resulting in planets being ejected from the system or colliding with one another. After the red giant phase, a star like our Sun will shed its outer layers, leaving behind a dense core known as a white dwarf. The remaining planetary system will be vastly different, with the habitable zone now located much closer to the white dwarf due to its lower luminosity. The long-term cooling of the white dwarf will continue to shift the habitable zone inward, affecting the potential for life on nearby planets. Overall, stellar evolution plays a crucial role in the dynamic and ever-changing nature of planetary systems. Understanding these processes helps astronomers predict the long-term habitability of planets and the potential for life to arise in different environments. Dark matter is a mysterious and invisible substance that plays a pivotal role in the dynamics of galactic collisions and mergers. Unlike normal matter, dark matter does not emit, absorb, or reflect light, making it undetectable through conventional electromagnetic observations. However, its presence is inferred through its gravitational effects on visible matter and the overall structure of galaxies. During galactic collisions, dark matter significantly influences the gravitational dynamics. As galaxies approach and interact, their dark matter halos, which are much more massive and extended than the galaxy's visible components, play a crucial role in the merger process. The gravitational pull of these halos helps to shape the trajectory and final configuration of the colliding galaxies. When galaxies merge, dark matter contributes to the formation of the resulting galaxy by affecting the distribution of stars, gas, and other materials. The dark matter halos can stabilize the merging galaxies, preventing them from fragmenting and helping to maintain the overall structure. The interactions between dark matter halos can also lead to the formation of new structures, such as tidal tails and bridges, which are observed in many merging galaxies. Furthermore, the presence of dark matter influences the star formation rates in merging galaxies. The additional gravitational forces can compress gas clouds, triggering bursts of star formation. This process, known as starburst activity, can produce large numbers of new stars in a relatively short period of time. Overall, dark matter is essential for understanding the dynamics of galactic collisions and the formation of new galaxies. Its gravitational influence shapes the outcomes of these cosmic events, contributing to the ongoing evolution and structure of the universe. Elliptical galaxies are often formed through the mergers and interactions of spiral galaxies. When galaxies collide and merge, the gravitational forces involved can disrupt their original disk structures, leading to the creation of a more spheroidal, elliptical shape. These interactions typically result in the mixing and redistribution of stars, gas, and dark matter. One of the key characteristics of elliptical galaxies is their older and redder star populations. This is because the violent merging process can trigger bursts of star formation, consuming much of the available gas and dust. Once the merger is complete, there is often little remaining gas to form new stars, leading to a population dominated by older stars. A prime example of this process is the predicted future merger between the Milky Way and the Andromeda Galaxy. Currently on a collision course, these two spiral galaxies are expected to merge in about 4.5 billion years. The resulting galaxy will likely be an elliptical galaxy, characterized by a less structured, more spheroidal shape and an older star population. This merger will significantly alter the structure and dynamics of both galaxies, leading to the formation of new star clusters and potentially reshaping the distribution of dark matter within the merged entity. Studying such mergers helps astronomers understand the evolutionary pathways of galaxies and the role of interactions in shaping the universe. Stars transition through various stages in their life cycle, starting with the red giant phase. In this stage, a star like our Sun expands as it exhausts hydrogen in its core, leading to the shedding of its outer layers through powerful stellar winds. This process enriches the surrounding interstellar medium with elements such as carbon and nitrogen. Following the red giant phase, the star enters the planetary nebula stage. During this phase, the expelled outer layers form a glowing shell of gas, illuminated by the central core that remains. This phenomenon creates a colorful display, marking the end of the star's life while releasing essential materials into space that contribute to future star and planet formation. The final stage is the white dwarf phase, where the exposed core cools and fades over billions of years. Although no longer undergoing nuclear fusion, white dwarfs exert significant gravitational influence on nearby celestial bodies, affecting their orbits. Over time, white dwarfs will eventually become black dwarfs, though the universe is still too young for any black dwarfs to exist yet. Each stage of stellar evolution, from the red giant to the planetary nebula to the white dwarf, plays a vital role in the cosmic cycle of matter. The materials ejected during these phases help seed new generations of stars and planetary systems, fostering continuous renewal and enrichment of the cosmos. When stars like our Sun reach the end of their lifespans, they enter a phase where they expel their outer layers into space. This process results in the formation of planetary nebulae, which are glowing clouds of gas and dust. As the star sheds its outer layers, the hot core left behind emits ultraviolet radiation that ionizes the expelled gas, causing it to glow in brilliant colors. These planetary nebulae are not only visually stunning but also play a crucial role in enriching the interstellar medium with essential elements. The gas and dust ejected from the dying star contain elements such as carbon, nitrogen, and oxygen, which are necessary for the formation of new stars and planetary systems. As the nebula expands and disperses its material into space, these elements mix with the surrounding interstellar medium, providing the raw materials for future star formation. The dispersion of elements from planetary nebulae contributes to the ongoing cycle of stellar evolution. The enriched material left behind by these nebulae eventually coalesces to form new generations of stars and planets, continuing the cosmic cycle of creation and destruction. This process highlights the interconnected nature of the universe, where the death of one star can lead to the birth of new celestial bodies. The future of Earth's climate patterns is significantly influenced by changes in its orbital characteristics and axial tilt, collectively known as Milankovitch cycles. These cycles, named after Serbian mathematician Milutin Milankovitch, include variations in eccentricity, axial tilt, obliquity, and precession. These factors affect the distribution and intensity of solar radiation reaching Earth's surface, which in turn drives long-term climate changes. Orbital eccentricity refers to the shape of Earth's orbit around the Sun, which ranges from more circular to more elliptical over a cycle of about 100,000 years. When Earth's orbit is more elliptical, the difference between the closest point, perihelion, and the farthest point, aphelion, from the Sun is greater, leading to more pronounced seasonal differences. These variations in solar radiation can influence the long-term climate, potentially triggering or mitigating periods of global warming or cooling. Axial tilt, or obliquity, is the angle between Earth's rotational axis and its orbital plane, which fluctuates over a cycle of approximately 41,000 years. Changes in axial tilt can affect the severity of the seasons. A greater tilt results in more extreme seasonal variations, while a lesser tilt leads to milder seasons. For example, during periods of higher axial tilt, polar regions receive more direct sunlight in the summer, leading to increased melting of ice sheets and glaciers. Conversely, during periods of lower axial tilt, summers are cooler, allowing ice sheets to grow and potentially contributing to the onset of ice ages. Precession, the wobble in Earth's rotational axis, occurs over a cycle of about 26,000 years, and affects the timing of the seasons in relation to Earth's position in its orbit. This can lead to shifts in the distribution of solar energy, further influencing long-term climate patterns. For instance, when the northern hemisphere is tilted toward the Sun at perihelion, it experiences warmer summers and colder winters, while the opposite is true when it is tilted away at aphelion. These combined effects of Milankovitch cycles contribute to the periodic changes in Earth's climate, including the alternating periods of glacial and interglacial epochs observed in geological records. During glacial periods, extensive ice sheets cover large parts of the northern hemisphere, while interglacial periods, like the one we are currently in, are characterized by warmer global temperatures and reduced ice cover. In addition to natural Milankovitch cycles, human activities have introduced a new dimension to climate change. The rapid increase in greenhouse gas emissions since the Industrial Revolution has led to unprecedented warming, which interacts with natural climate drivers in complex ways. Understanding the interplay between these human-induced changes and natural cycles is crucial for predicting future climate trends. Overall, the future of Earth's climate patterns will be shaped by the intricate interplay of natural cycles and anthropogenic influences. By studying past climate changes and understanding the mechanisms driving them, scientists can improve climate models and develop strategies to mitigate the impacts of global warming. This knowledge is essential for informing policy decisions and ensuring a sustainable future for our planet. Gravitational waves, ripples in spacetime caused by the acceleration of massive objects, were first predicted by Albert Einstein's theory of general relativity in 1915. These waves propagate at the speed of light, carrying energy away from their sources. Among the most significant and detectable sources of gravitational waves are merging supermassive black holes, which reside at the centers of galaxies. When galaxies collide, their central supermassive black holes eventually merge, creating an incredibly energetic event. As these black holes spiral toward each other, they emit gravitational waves, losing energy and gradually drawing closer together. The final moments of this dance, where the black holes coalesce, generate intense gravitational waves that can be detected across vast distances. The detection of gravitational waves from galactic mergers offers a unique window into the universe. These waves provide valuable insights into the dynamics of massive celestial bodies, revealing details about their masses, spins, and the nature of their interactions. The observation of gravitational waves complements traditional electromagnetic observations, such as visible light, X-rays, and radio waves, allowing astronomers to gain a more comprehensive understanding of cosmic events. The first direct detection of gravitational waves was achieved by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015. This groundbreaking discovery confirmed the existence of gravitational waves and opened a new era in astronomy. LIGO, along with the Virgo Interferometer in Europe, has since detected numerous gravitational wave events, including those from binary black hole mergers and neutron star collisions. Gravitational waves from supermassive black hole mergers are typically in the low frequency range, making them suitable targets for space-based detectors like the upcoming Laser Interferometer Space Antenna, LISA. Scheduled for launch in the 2030s, LISA will consist of 3 spacecraft arranged in a triangular formation, separated by millions of kilometers. This configuration will allow LISA to detect low-frequency gravitational waves with unprecedented sensitivity, providing insights into the most massive black hole mergers in the universe. The study of gravitational waves from galactic mergers has several important implications for our understanding of the cosmos. Mass and spin of black holes. Gravitational wave signals carry information about the masses and spins of the merging black holes. By analyzing these signals, scientists can determine the properties of black holes and gain insights into their formation and evolution. Galaxy evolution. The mergers of supermassive black holes are often accompanied by mergers of their host galaxies. Studying these events helps astronomers understand the processes that drive galaxy formation and evolution, including the role of mergers in triggering star formation and shaping galactic structures. Testing general relativity. Gravitational waves provide a direct test of Einstein's theory of general relativity. Observations of the waveforms and their behavior during the merger process can confirm or challenge the predictions made by general relativity about the nature of gravity. Cosmology. Gravitational waves allow astronomers to probe the population of black holes in the universe. By studying the frequency and distribution of black hole mergers, scientists can understand the history and evolution of galaxies and the role of black holes in shaping them. Detecting and interpreting gravitational waves from supermassive black hole mergers present several challenges. The low-frequency signals require highly sensitive detectors and sophisticated data analysis techniques to distinguish them from background noise. Accurately modeling the waveforms of merging black holes involves complex simulations that take into account the effects of general relativity and the dynamics of the black hole's interactions. Gravitational waves from galactic mergers provide a powerful tool for exploring the dynamics of massive celestial bodies and the fundamental nature of gravity. As technology advances and observatories like LISA come online, we can look forward to even more profound discoveries that will deepen our understanding of the universe and its fundamental forces. Shifts in orbital eccentricity, the measure of how much an orbit deviates from being circular, occur due to gravitational interactions and other forces acting on planets over long periods. These variations can significantly influence the climate and stability of planetary systems, shaping the environments of the planets within them. Orbital eccentricity is affected by the gravitational pull of other planets, moons, and even passing stars. In a planetary system, such as our own solar system, the gravitational interactions between planets can lead to changes in their orbits. For example, the gravitational influence of Jupiter, the largest planet in our solar system, can alter the orbits of other planets, causing their eccentricities to change over time. This process is known as orbital perturbation and can lead to long-term variations in the shape and orientation of planetary orbits. These changes in orbital eccentricity have a direct impact on the climate of a planet. A more eccentric orbit means that the distance between the planet and its star varies more significantly over the course of a year. This variation affects the amount of solar energy the planet receives, leading to more extreme seasonal changes. For instance, when Earth's orbit becomes more eccentric, it experiences greater differences in temperature between summer and winter, which can contribute to the onset of ice ages and other long-term climate changes. Moreover, shifts in orbital eccentricity can influence the stability of planetary systems. Highly eccentric orbits can lead to close encounters between planets, increasing the risk of collisions or ejections from the system. These interactions can disrupt the overall architecture of the system, leading to a reorganization of planetary orbits. In some cases, planets may be flung into highly elongated orbits or even entirely out of the system, altering the dynamics and stability of the remaining planets. The study of orbital eccentricity and its effects is crucial for understanding the long-term evolution of planetary systems and the potential habitability of planets. By analyzing the orbits of exoplanets and their changes over time, astronomers can gain insights into the dynamics of these distant systems and assess their stability and climate conditions. This knowledge helps identify potentially habitable planets and understand the processes that shape the diversity of planetary environments. Shifts in orbital eccentricity are driven by gravitational interactions and have significant implications for the climate and stability of planetary systems. These changes influence the distribution of solar energy on planets, leading to variations in climate and seasonal patterns, and can affect the overall architecture and stability of planetary systems. Understanding these processes is essential for studying the long-term evolution and habitability of planets within our solar system and beyond. The evolution of planetary atmospheres is a complex and dynamic process influenced by various factors, such as solar radiation, volcanic activity, and interactions with the space environment. Understanding these factors is crucial for determining a planet's habitability and climate. One of the primary influences on atmospheric evolution is solar radiation. The energy emitted by a star affects the temperature and chemical reactions within a planet's atmosphere. For example, ultraviolet, UV, radiation from the sun can break down molecules in the upper atmosphere, leading to the formation of ozone in Earth's stratosphere. This ozone layer is essential for protecting life on the surface by absorbing harmful UV radiation. Changes in solar radiation over time can significantly impact atmospheric composition and temperature, driving long-term climate changes. Interactions with the space environment, including impacts from comets and asteroids, also play a role in atmospheric evolution. These collisions can introduce new materials and gases into the atmosphere, altering its composition. For example, the late heavy bombardment period in the early solar system is believed to have delivered water and other volatile compounds to Earth, contributing to the development of its oceans and atmosphere. Atmospheric escape, the loss of atmospheric gases to space, is another critical process influencing the evolution of planetary atmospheres. This can occur through thermal escape, where lighter gases like hydrogen and helium achieve escape velocity due to high temperatures, or through non-thermal processes, such as solar wind stripping. Mars, for instance, has experienced significant atmospheric loss over billions of years, leading to its current thin and mostly CO2 atmosphere. The lack of a strong magnetic field on Mars has made it more vulnerable to solar wind stripping compared to Earth, which is protected by its magnetic field. The interplay between these factors determines the long-term stability and composition of a planet's atmosphere. On Earth, the presence of a stable atmosphere with a balanced composition of nitrogen, oxygen, and trace gases has been crucial for maintaining a climate that supports life. The evolution of Earth's atmosphere has been influenced by a combination of solar radiation, volcanic activity, biological processes, and interactions with the space environment. The study of planetary atmospheres extends beyond our solar system to exoplanets. By analyzing the atmospheres of distant planets, scientists can infer their potential habitability and climate conditions. Observations from telescopes, such as the James Webb Space Telescope, JWST, provide valuable data on the composition and structure of exoplanet atmospheres, offering insights into their evolution and the possibility of life beyond Earth. The evolution of planetary atmospheres is shaped by a complex interplay of factors, including solar radiation, volcanic activity, and atmospheric escape. Understanding these processes is key to determining a planet's habitability and climate, both within our solar system and beyond. Advances in telescopic technology have revolutionized our ability to observe and understand distant cosmic events and phenomena, ushering in a new era of astronomical discovery. Modern telescopes, both ground-based and space-based, offer unprecedented resolution and sensitivity, allowing scientists to peer deeper into the universe than ever before. Among these instruments, the James Webb Space Telescope, JWST, stands out as a particularly groundbreaking tool that promises to significantly enhance our understanding of the cosmos. The JWST, launched in December 2021, is the most powerful space telescope ever built. It features a 6.5-meter diameter primary mirror, composed of 18 hexagonal segments, which provides it with extraordinary light-gathering capability. The telescope operates primarily in the infrared part of the spectrum, which is crucial for observing distant objects whose light has been redshifted due to the expansion of the universe. This allows JWST to peer back in time to observe the first galaxies that formed after the Big Bang, offering insights into the early stages of cosmic evolution. One of the key scientific goals of the JWST is to study the formation and evolution of galaxies. By observing galaxies at different stages of their development, astronomers can piece together the processes that have shaped them over billions of years. JWST's infrared capabilities enable it to see through dust clouds that obscure visible light, revealing the hidden structures and star-forming regions within galaxies. This helps scientists understand the role of dark matter, supermassive black holes, and other factors in galactic evolution. In addition to studying galaxies, JWST is designed to explore the atmospheres of exoplanets. By analyzing the starlight that passes through a planet's atmosphere as it transits in front of its host star, the telescope can detect the chemical signatures of various molecules, such as water vapor, carbon dioxide, and methane. This information is crucial for assessing the habitability of exoplanets and searching for potential signs of life beyond our solar system. Beyond JWST, future telescopic missions are set to further expand our observational capabilities. The European Space Agency's Euclid mission, scheduled for launch in 2022, aims to map the geometry of the dark universe by studying dark matter and dark energy. By measuring the shapes, positions, and redshifts of billions of galaxies, Euclid will help unravel the mysteries of these elusive components that make up most of the universe's mass and energy. Another exciting future mission is the Nancy Grace Roman Space Telescope, formerly known as WFIRST, set for launch in the mid-2020s. Named in honor of NASA's first chief of astronomy, this telescope will have a field of view 100 times larger than the Hubble Space Telescope, allowing it to conduct wide-field surveys of the universe. The Roman Space Telescope will study phenomena such as dark energy, exoplanets, and the structure of the Milky Way, contributing to our understanding of the universe's expansion and the distribution of galaxies. Ground-based telescopes are also undergoing significant advancements. The Extremely Large Telescope, ELT, currently under construction in Chile, will have a 39-meter primary mirror, making it the largest optical/near-infrared telescope in the world. Scheduled to begin operations in the late 2020s, the ELT will provide unprecedented resolution and sensitivity, enabling detailed studies of distant galaxies, star formation, and exoplanets. These modern telescopic technologies, combined with future missions, are set to transform our understanding of the cosmos. By enabling detailed observations of distant cosmic events and phenomena, they provide invaluable insights into the fundamental processes that shape the universe. As we continue to push the boundaries of observational astronomy, we can expect to uncover new and exciting discoveries that will deepen our comprehension of the universe and our place within it. The solar wind, a stream of charged particles, mainly protons and electrons, emitted by the Sun, plays a significant role in shaping the atmospheres and surface conditions of planetary bodies within our solar system. This constant flow of particles can have profound effects, particularly on those planets and moons that lack strong magnetic fields to protect them. One of the primary impacts of the solar wind is atmospheric stripping. When the charged particles from the solar wind collide with the upper layers of a planet's atmosphere, they can impart enough energy to atmospheric particles to escape the planet's gravitational pull. Over long periods, this process can lead to significant atmospheric loss, altering the climate and surface conditions of the affected body. Mars is a prime example of a planet that has experienced substantial atmospheric loss due to solar wind. Billions of years ago, Mars is believed to have had a thicker atmosphere and the presence of liquid water on its surface. However, the loss of its global magnetic field, which occurred around 4 billion years ago, left its atmosphere vulnerable to the erosive effects of the solar wind. As a result, Mars has lost much of its atmosphere, leading to the cold, arid environment we observe today. The MAVEN, Mars Atmosphere and Volatile Evolution, mission has provided valuable data on how the solar wind interacts with and strips away the Martian atmosphere. Venus, despite having a thick atmosphere primarily composed of carbon dioxide, also experiences significant interaction with the solar wind. Although Venus does not have a global magnetic field, it possesses an induced magnetosphere created by the interaction between the solar wind and its ionosphere. This induced magnetosphere helps protect the planet to some extent, but it is less effective than Earth's magnetic field. Consequently, the solar wind still contributes to atmospheric erosion, particularly of lighter elements like hydrogen, which can escape into space. Planets and moons with strong magnetic fields, like Earth, are much better protected from the solar wind. Earth's magnetic field deflects the charged particles, creating a protective bubble known as the magnetosphere. This shield prevents most of the solar wind from directly reaching the atmosphere, preserving its density and composition. The interaction between the solar wind and Earth's magnetosphere can still cause spectacular phenomena such as the auroras, which occur when charged particles are funneled toward the polar regions and interact with the upper atmosphere, producing brilliant light displays. On the other hand, moons and smaller bodies lacking significant atmospheres or magnetic fields, such as the Moon and Mercury, are more directly exposed to the solar wind. This exposure can lead to the sputtering of surface materials, where atoms are ejected from the surface due to the impact of solar wind particles. Over time, this process can alter the surface composition and create thin, transient atmospheres known as exospheres. Understanding the impact of the solar wind on planetary bodies is crucial for assessing their potential habitability. The presence or absence of a protective magnetic field plays a significant role in determining a planet's ability to retain its atmosphere and sustain conditions favorable for life. Future missions to study planetary atmospheres and magnetic fields will continue to provide insights into the complex interactions between the solar wind and celestial bodies. The solar wind exerts a profound influence on planetary atmospheres and surface conditions, particularly on those without strong magnetic fields. Through atmospheric stripping and surface sputtering, the solar wind shapes the environments of these bodies, influencing their climate and potential habitability. Understanding these processes is essential for exploring the past, present, and future conditions of planets and moons in our solar system and beyond. Long-term changes in the solar system's structure are driven by gravitational interactions among its various components and the evolving mass of the Sun. These changes, occurring over billions of years, have a profound influence on the architecture of the solar system, affecting the orbits of planets, moons, and smaller bodies. One of the primary forces shaping the solar system is the gravitational interactions between its constituents. Each planet exerts gravitational forces on other planets, leading to subtle changes in their orbits over time. For example, Jupiter, the most massive planet in our solar system, has a significant influence on the orbits of other planets. Its gravitational pull can cause shifts in orbital eccentricity, inclination, and even semi-major axes of other planets, leading to long-term variations in their positions. Another critical factor is the Sun's gradual loss of mass. Over time, the Sun loses mass through the emission of solar wind and the expulsion of high-energy particles. As the Sun's mass decreases, its gravitational pull on the planets weakens slightly. This gradual reduction in gravitational force causes the orbits of the planets to expand slowly. For instance, Earth's orbit will gradually move outward as the Sun loses mass, although this change is extremely slow and takes place over billions of years. The solar system's structure is also influenced by the migration of planets. Early in the solar system's history, the giant planets, Jupiter, Saturn, Uranus, and Neptune, underwent significant migration. According to the NICE model, these planets initially formed closer to the Sun and then moved to their current positions. This migration had profound effects on the distribution of smaller bodies, such as asteroids and comets, and contributed to the Late Heavy Bombardment, a period of intense comet and asteroid impacts on the inner planets. In addition to planetary migration, gravitational interactions between planets and smaller bodies, such as asteroids and Kuiper belt objects, lead to changes in the orbits of these smaller bodies. Resonances with the giant planets can cause certain orbits to become unstable, resulting in the scattering of these bodies throughout the solar system. For example, the Kirkwood gaps in the asteroid belt are regions where the gravitational influence of Jupiter creates resonances that clear out asteroids, preventing them from maintaining stable orbits in those areas. Over extremely long timescales, the solar system may also be affected by interactions with other stellar systems. As the Sun orbits the center of the Milky Way galaxy, it passes through different regions with varying densities of stars and interstellar matter. Close encounters with other stars, though rare, can perturb the orbits of outer solar system objects, such as those in the Oort cloud, potentially sending comets into the inner solar system. The future evolution of the solar system will be marked by the Sun's life cycle. As the Sun exhausts its nuclear fuel, it will expand into a red giant, engulfing the inner planets, including possibly Earth. Following the red giant phase, the Sun will shed its outer layers, creating a planetary nebula, and leaving behind a dense white dwarf. The loss of mass during these stages will significantly alter the gravitational dynamics of the remaining planets, potentially leading to further changes in their orbits. The solar system's structure is continuously evolving due to gravitational interactions, the Sun's mass loss, planetary migration, and encounters with other stellar systems. These changes, unfolding over billions of years, reshape the architecture of the solar system and influence the orbits and stability of its constituent bodies. Understanding these long-term changes helps scientists gain insights into the dynamic nature of planetary systems and their evolution. The life and death of stars in the universe are fundamental processes that shape cosmic evolution and drive the creation of new celestial bodies. Stars are born in vast clouds of gas and dust known as nebulae, where regions of higher density collapse under gravity to form protostars. As these protostars accumulate mass and their cores heat up, nuclear fusion ignites, marking the birth of a new star. Stars spend the majority of their lives in the main sequence phase, where they fuse hydrogen into helium in their cores. The duration of this phase depends on the star's mass. More massive stars burn through their fuel quickly and have shorter lifespans, while smaller stars, like red dwarfs, can remain in the main sequence for billions of years. As stars exhaust their hydrogen fuel, they evolve into different stages depending on their initial mass. For Sun-like stars, this transition leads to the red giant phase, where the core contracts and heats up, causing the outer layers to expand and cool. Eventually, the outer layers are expelled, forming a planetary nebula, while the remaining core becomes a white dwarf. White dwarfs slowly cool and fade over billions of years, representing the final stage of stellar evolution for these stars. Massive stars, on the other hand, undergo more dramatic transformations. After exhausting hydrogen, they begin to fuse heavier elements in their cores, creating layers like an onion. When the core accumulates iron, fusion stops because iron cannot release energy through fusion. This leads to a catastrophic core collapse, resulting in a supernova explosion. The supernova disperses elements formed in the star into space, enriching the interstellar medium with heavy elements such as carbon, oxygen, and iron. These elements are essential for the formation of new stars, planets, and even life. The remnants of a supernova can form either a neutron star or a black hole, depending on the initial mass of the star. Neutron stars are incredibly dense, composed mostly of neutrons, while black holes are regions of spacetime where gravity is so strong that not even light can escape. These remnants continue to interact with their surroundings, influencing the dynamics of galaxies and contributing to the complex tapestry of the universe. The elements dispersed by dying stars play a crucial role in cosmic evolution. They mix with existing gas and dust, providing the raw materials for new generations of stars and planets. This cycle of star birth, evolution, and death is essential for the ongoing renewal of the cosmos, driving the formation of diverse and complex structures throughout the universe. Understanding the life cycles of stars not only provides insights into the processes that shape the universe but also helps us comprehend the origins of the elements that make up everything around us. From the calcium in our bones to the iron in our blood, many of the elements essential for life were forged in the hearts of stars and spread throughout the galaxy by stellar winds and supernova explosions. The study of stellar evolution continues to be a central focus of astronomy, with modern telescopes and observatories providing detailed observations of stars at various stages of their life cycles. These observations help refine our models of stellar behavior and improve our understanding of the universe's history and future. We'd love to hear your thoughts in the comments below. If you enjoyed this video and found it informative, please like, share, and subscribe for more fascinating content. Thank you for journeying with us here on Frontiers of Infinity.